Welcome to a screencast on buffers. First of all, let's define what a buffer is. And a chemical buffer is a solution that resists changes in pH when you add either an acid or a base to that solution. For example, if this is a buffer solution, maybe it's a buffer solution with a pH of 5.00. If we were to add some acid to that buffer, what would end up happening is the pH of the buffer would decrease, but just a little bit. We're adding some acid. We'd expect the pH to go down when we add acid, but it doesn't go down very much, maybe to 4.9 or something. Now, conversely, if we have the same buffer and instead we add to it some base, then adding base makes the pH increase. But again, if it's a buffer solution, the pH doesn't increase very much. Maybe it goes up to 5.12, for example. So buffers are substances or solutions that resist changes in pH when either acid or base is added to the buffer solution. Now, what makes up a buffer? Well, a buffer contains reasonably equal amounts of a weak acid and its conjugate base. So, for example, we could have acetic acid, the weak acid, and the conjugate base of acetic acid, the acetate ion, and that makes up a buffer. And buffers in general function best when the pH of the buffer is close to the pKa of the weak acid that's involved in the buffer. So in the case of this buffer, where we have some weak acid, acetic acid, and its conjugate base, the acetate ion, the K sub A for acetic acid is 1.8 times 10 to the minus fifth. The pKa is then negative log of the Ka, or negative log of 1.8 times 10 to the minus fifth, and that's about 4.74. And so if you make a buffer with acetic acid and acetate, then you'd like it to have a pH, give or take, maybe about 1 pH unit of 4.74. So typically you'd want your acetate acetic acid buffer to have a pH between maybe 3.7 and 5.7 or so for it to buffer acid and base relatively equally. One other note is the acetate ion in the acetic acid buffer typically would come from maybe a sodium acetate or potassium acetate solution or compound. Here we're only showing the important ion, the acetate ion. There will, of course, have to be some counter ions, some positive ions in the solution to balance that out, but they're spectator ions, so we typically will ignore them. Okay, so here are a couple of solutions, and actually there's going to be 3 solutions, and let's determine whether or not they are buffer solutions. And the first one is a mixture of hydrofluoric acid, HF, and potassium fluoride, KF, and 0.3 molar of each of those in the solution. Well, HF is a weak acid, so that's one of the important things for a buffer. F minus is the conjugate base of HF, and that's one of the other important things for a buffer. So we have a weak acid and its conjugate base, so that's good. And the concentrations of HF and KF, or F minus, is what really matters. Those concentrations are equal, so we have a weak acid with its conjugate base in equal concentrations, and that meets the criteria for a buffer. So yes, this is a buffer solution. Okay, the next one. 0.5 molar HCl mixed together with 0.5 molar NaCl. Is this a buffer solution? HCl is a strong acid. Cl minus from the NaCl is its conjugate base, and the concentrations of the two the two substances, HCl and Cl minus, are equal. So we have 2 out of the 3 things needed for a buffer, but HCl being a strong acid means we don't have a buffer. It has to be a weak acid, so even though we have the conjugate base and relatively equal concentrations, this is not a buffer because HCl is not a weak acid. And one more, 0.25 molar acetic acid and 0.5 molar potassium acetate. So we have acetic acid, which is a weak acid. We have the acetate ion, which is the conjugate base of acetic acid. That's from the potassium acetate part of the solution. And although the 0.25 molar and 0.5 molar concentrations of these two substances aren't equal, in fact, are a factor of 2 different, those concentrations are considered similar enough for us to have a buffer. So we have a weak acid, we have its conjugate base, both of which are needed for a buffer, and then the factor of 2 difference in the concentrations of these two components is not disqualifying. In fact, we would consider it a buffer even if the two concentrations differ by a factor of 10, possibly even more, but 10 is usually kind of the normal limit used for this. So yes, this is a buffer solution, even though the concentrations are not equal, they're close enough. Okay, now moving on from definition of a buffer and how it functions to some mathematical relationships and ultimately some calculations. If we have a generic buffer system, HA with A minus, so HA is our weak acid, A minus is its conjugate base, and here's maybe a picture of what that might look like. We've got a mixture of some weak acid and some conjugate base, and at any given instant, if there's our buffer solution sitting around, we have an equilibrium between the weak acid and its conjugate base. There will be a little bit of hydrogen ion or hydronium ion in there and a little bit of hydroxide ion, but the main solution components are the weak acid and its conjugate base. And then just as a reminder, the weak acid has a K sub A value that's given by this relationship, H3O plus times A minus over HA concentration. Okay, well, it turns out that this equation can be rearranged mathematically, and we can, when we do that, come up with the following relationship. pH equals pKa plus log base 10 of the ratio of the conjugate base concentration, A minus, over the acid concentration, HA. This relationship is known as the Henderson-Hasselbalch equation. It's a shortcut way to calculate pH of a buffer solution. It's actually an approximation. It's a very good approximation when we're dealing with a buffer. It's not at all a good thing to use if we do not have a buffer. And one other note is we could totally skip this Henderson-Hasselbalch equation and do a buffer calculation only using the K sub A and ice tables, but oftentimes we want a quicker way to get to the result, and so we can skip some of the math or some of the more complicated math, the more time-consuming math, and use this relationship, the Henderson-Hasselbalch equation, and again, only applies to buffers, not to other things. Okay, so here is a problem involving a buffer pH calculation. We're asked to calculate the pH of a buffer made by combining 50 milliliters of 3 molar acetic acid with 14.28 grams of sodium acetate in enough water to make 250 milliliters of solution. And this is a typical way to make a buffer. We take some weak acid, in this case acetic acid. We take some of its conjugate base, in this case the acetate ion, which comes from some sodium acetate. We mix them together in a container, add enough water to make our particular volume we're interested in, and then that solution will have a particular pH. We can calculate this pH using the buffer equation or the Henderson-Hasselbalch equation, and we remember we're going to need to know the pKa, which means we need to know the Ka of the weak acid, and that is typically a value can be found in tables. For acetic acid, the Ka is 1.8 times 10 to the minus fifth, and then we're going to need to determine the concentration of the acetate ion and the concentration of the acetic acid, and then put these all into our equation and see what kind of pH value we get. Well, let's start by calculating the acetic acid concentration. and we note that we have 50 milliliters or 0.050 liters of 3 molar acetic acid, which is 3.00 moles per liter. So that product, 0.0500 liters times 3.00 moles per liter, will give us the number of moles of acetic acid. And now it's been diluted into 250 milliliters or 0.25 liters of solution. So that gives us 0.150 moles of actual acetic acid in 0.250 liters of solution, and that works out to be a concentration of 0.600 molar acetic acid. We'll do the same thing with the acetate ion, and we need to note that we have 14.28 grams of sodium acetate, so we need the molar mass of sodium acetate, about 82 grams per mole. We do the grams divided by grams per mole will give us the moles of sodium acetate, and of course the moles of sodium acetate is going to be the same as the moles of the acetate ion, and then we'll ignore the sodium ion, and then that number of moles of acetate will also be in the 250 milliliters of solution. So that works out to be 0.174 moles of acetate ion in 0.250 liters of solution, and that gives us a molarity of the acetate ion of 0.696 molar. Okay, we now have our K sub A value. We have our concentration of both species in the buffer, so we can plug into the equation negative log of 1.8 times 10 to the minus fifth is the pKa value. Log of acetate ion concentration over acetic acid concentration. And notice this is a ratio of molarities, so the units of molarity cancel. Negative log of 1.8 times 10 to the minus fifth is 4.74. Log of this ratio, 0.696 over 0.6, works out to be not much bigger than 0.06. And then we add those together, and we have 4.80 as the pH of this particular buffer with these particular amounts of acetic acid and sodium acetate. Now, what if we add some acid or base to this buffer? What happens to the pH? Can we calculate that? And in this case, we're going to add some strong acid, some hydrochloric acid, 50 milliliters of 1 molar hydrochloric acid. What's the pH of the resulting solution? Well, here is a representation of our buffer solution. We have some acetic acid and some acetate ions. We have, if you remember from the previous calculation, 0.150 moles of acetic acid and 0.174 moles of acetate ion. And here we're using moles rather than molarity because reactions take place on a mole-to-mole basis, and we're going to have some reaction between the added hydrochloric acid and something in our buffer. Well, when we add H3O+, we're going to be adding some H+ ion or H3O+ from the HCl. What's that going to react with? Well, the base, the acetate ion, that part of the buffer is what buffers against added acid. So this conjugate base, this acetate ion, will react with added H3O+ to produce some of the conjugate weak acid, acetic acid, and water. And that reaction we can sort of visualize here. We add some H+ ion, and that substance adds on to, sticks to an acetate ion and makes some acetic acid. And if we add a little bit more H+, it's going to add on to another acetate ion and make some acetic acid. Now notice what's happened is we now have more acetic acid molecules or moles. We have less acetate ion molecules, but we still have some of each, or if we do still have some of each, then we still have a functioning buffer. So let's calculate and see what happens. So here is our reaction, and we've added 0.0500 moles of H3O+, so 50 milliliters or 0.05 liters times 1 mole per liter gives us that amount of moles of H3O plus that's added. And we can actually treat the reaction that occurs using essentially an ice table. And this time, though, we need to work in moles rather than molarity because the reaction takes place on a mole-to-mole basis. So we have 0.174 moles of the acetate ion in our original buffer. We've added to that 0.0500 moles of hydronium ion, or H+. We originally had 0.150 moles of acetic acid, and water we're not going to really care about because there's a whole bunch of that around. It's in excess. Its concentration doesn't change very much during this process. Okay, so what's the change? And in this case, the change will be the reaction that takes place, and we're not going to mess around with plus X and minus X because this is a single arrow. Really, it's a double arrow with a little bit of from the right to the left arrow, but mostly because acetic acid's a weak acid, it's mostly associated. So if we throw in some H3O plus or H plus, it's going to mostly associate with the acetate ion and mostly make acetic acid. And so the little bit of plus X and minus X that we normally deal with in equilibrium calculations, we can actually dispense with here. We just do the bulk reaction. And essentially, all of the H3O plus reacts. That means that the acetate ion the acetate ion number of moles will go down by the same amount as the H3O plus does because it's a 1-to-1 ratio. And the acetic acid number of moles will go up by the same amount. So at our essentially end point of the reaction, we can call it our equilibrium, but at the end point of the reaction, our acetate ion goes down to 0.124 moles. Our H3O plus goes to pretty close to 0. We'll see it's not exactly 0, but it's very small by comparison to everything else. And our acetic acid goes up to 0.2 moles. And again, water we don't really care about. So notice we still have some acetate left. Notice we now have more acetic acid, but we still have some of both of the weak acid and its conjugate base. So we still have a buffer. And we can still use the buffer equation, but we should maybe also note that by adding 50 milliliters of solution to 250 milliliters of solution, we now have 300 milliliters of solution, or 0.3 liters. And so our new concentration of acetate ion is 0.124 moles over 0.300 liters. And similarly, our new concentration of acetic acid is 0.200 moles over 0.300 liters. And we can use the buffer equation again. And once again, pKa is the negative log of the Ka for the weak acid. And here, explicitly writing out the whole ratio of the moles per liter of the acetate ion concentration and the moles per liter of the acetic acid concentration. And note, since both the solution or both substances are in the same solution, the volume for each is going to be the same, and so the molarity ratio and the mole ratio actually ends up being the same thing when we're dealing with a buffer. That's not always going to be true for everything in the world, but for buffers, because they're in the same solution, then that molarity ratio and mole ratio being equal, that holds true. And so our molarities, when we divide the moles by liters, for the acetate we get 0.413 molar. For the acetic acid we get 0.667 molar. And we can then plug those values into our equation. And whether we use the molarity ratio or the mole ratio, we get log of 0.62 as what is added on to the 4.74, which was the pKa of acetic acid. And when we combine those two together, we get 4.53 for the pH of this solution after we've added the hydrochloric acid. Now, if you remember, the original buffer solution had a pH of 4.80. This has a pH now of 4.53, so the pH has decreased a little bit due to the added strong acid, and that's kind of what we would expect. One other thing to note is we've been saying the H3O plus concentration is about 0. Well, clearly it's not 0 because we have a pH of 4.53, so there has to be some hydronium ion. And if we calculate the amount of hydronium ion we have from the pH, we get 3.0 times 10 to the minus 5th molar. So notice that's not 0, but it's very small by comparison to either of the concentrations of the weak acid and its conjugate base. So that's part of the buffer calculation approximation. And then one last thing to note, we could do essentially the same process, but somewhat in reverse, if instead of adding strong acid to a buffer, we added strong base. In that case, the thought process would be very similar, except instead of combining the strong acid with the conjugate base part of the buffer, we'd be adding strong base like hydroxide ion, and that would react with the acetic acid, the weak acid part of the buffer, and otherwise similar type of calculations would occur. So that is it for the Buffers screencast.